The next one is number 8, and here we have a non-zero ring A, and we have to show that the set of all prime ideals of A has minimal elements with respect to inclusion. Any such element is of course itself also a prime ideal, and it's minimal in the sense that you won't find another prime ideal which is contained inside of it as a proper subset. So we have to prove that such minimal elements exist. So we start off the solution by giving a name to this collection of prime ideals. Let K be the set of all prime ideals of A. And note this fact that since A is non-zero, A is not the zero ring, you go to the statement of theorem 1.3, you would understand how. Theorem 1.3 implies that K is non-empty. This means that our ring has at least one prime ideal. Alright. Now it seems that we should use Zorn's lemma here. However, Zorn's lemma gives us maximal elements, not minimal elements. So what can we do? We can still apply Zorn's lemma but with a trick. And that trick is this. We define this relation on our collection K as follows. For any two P and Q in K, that means these are prime ideals, we define P to be greater than or equal to Q if we call this greater than or equal when, that is, if P is contained in Q. Actually, you view Q as the larger one here, but say we decide to call P larger in this new relation. We now aim to show that this relation is a partial order relation on our collection K, and for which we need to show three things: that the relation is reflexive, antisymmetric, and transitive. So we take any three elements P, Q, and R in K, that means these are prime ideals of A. Because P is a subset of itself, by the above definition, P is greater than or equal to P. So that means our relation is reflexive. Next, assume that P is greater than or equal to Q and Q is also greater than or equal to P. This means that Q is a subset of P, and this means that P is a subset of Q. So P and Q are equal as sets, and that's how our relation is antisymmetric. And finally, we assume this and this. P is greater than or equal to Q, which is greater than or equal to R. But this means that Q is a subset of P, and this means that R is a subset of Q. And that is why you already know these things, that R is a subset of P. And because of that, P is greater than or equal to R. So our relation is transitive as well, and that's why it's a partial order on K. So now our collection K has become a partially ordered set with respect to this relation. Now to be able to apply Zorn's lemma, we need to still show that every chain in K has an upper bound in K. So accordingly, we let K prime be a chain in K. And now we want to produce an upper bound for this chain in K. What is a chain? Recall that a chain in a partially ordered set is a totally ordered subset of it. That means, in a general partially ordered set, if you choose any two elements, they may not be comparable, which you can see here for yourself. I mean, if you just arbitrarily choose two prime ideals, it's not necessary that one of them is a subset of the other. None of them may be a subset of the other. However, in a chain, any two elements are comparable. So K prime is one such chain. And now, next we consider this. K prime as a subset of K will have what? Ultimately, it will have prime ideals. So we collect all those prime ideals and consider their intersection and call that intersection P. Our idea is to show that this P is actually going to be an upper bound for this chain K prime. And not just an upper bound, I mean it needs to be in K. Now here is something we already know about this P, namely the fact that it's an ideal of A, because any intersection of ideals, the intersection of any collection of ideals is itself an ideal. But that alone does not make it an element of K, because it needs to be a prime ideal. Next, that is what we are going to show. So to prove that, next we take two elements A and B in our ring A such that their product AB belongs to P. What is it that we have to show? We have to show that then either A belongs to P or B belongs to P. If we can show this, then that would mean that P is a prime ideal. But suppose that's not true, that neither A nor B belongs to P. What does that mean? Because P by definition is this intersection, A not being an element of P means that A is not in at least one P prime coming from K prime. So that means there exists a P1 prime in K prime such that A is not inside P1 prime. Similarly, because B is not in P, there is some P2 prime in K prime which does not contain B as an element. This P1 prime, P2 prime may be same, may be different, we don't really know, but they exist. Next, let us see this line. Since AB belongs to P1 prime and AB also belongs to P2 prime, we must have A as an element in P2 prime and B as an element in P1 prime. How? Well, first of all, where are these things coming from? These things are coming from here. Because AB belongs to P and P is this intersection, so automatically AB would belong to every set that has been considered in this intersection. In particular, AB would belong to P1 prime and P2 prime because they are coming from K prime. So they are also included in this intersection. So that's how we have this and this. Alright. Now you recall that P1 prime, recall means you already see that here, P1 prime is an element of K prime. And what is K prime? K prime is a chain in K. So ultimately it's a subset of K. That makes P1 prime an element of K. That is, P1 prime is a prime ideal. So AB being an element of P1 prime means that either A belongs to P1 prime or B belongs to P1 prime. At least one of these two things has to be true. But A already is not an element of P1 prime. So that forces B to be an element of P1 prime. Because otherwise the primality of P1 prime would be violated. In a similar manner from this one and the fact that P2 prime is also a prime ideal of A, you get this, that A belongs to P2 prime. And now next you invoke the fact that K prime is a chain. As I said moments ago, that in a chain any two elements are comparable. So P1 prime and P2 prime being elements of K prime are also comparable. Comparable means what? Comparable, well, actually it means that either P1 prime is greater than or equal to P2 prime, where greater than or equal to is that relation that we defined for this solution, or P2 prime is greater than or equal to P1 prime. But I did not write that. In fact, I wrote what the meaning in fact is. That is, in place of P1 prime greater than or equal to P2 prime, I straight away wrote what it means. That P1 prime is a subset of P2 prime or P2 prime is a subset of P1 prime. One of these two things would happen. Now say the first inclusion is true, that P1 prime is a subset of P2 prime. But then what happens? Then you consider this thing, that B is an element of P1 prime. This inclusion would make B also an element of P2 prime, which is a contradiction to what? To this. B is not an element of P2 prime. And you would get a similar contradiction if you assume this one instead. So we are stuck here, and that just simply means that our earlier supposition is wrong. Let me just write that part. So this is how we write. So our last supposition is wrong. What was our supposition? That neither A nor B belongs to P, which is thus wrong. That means A is in P or B is in P or both. But that just makes P a prime ideal, i.e. P is now finally P is an element of K. Next we note this, that P is a subset of P prime for all elements P prime in K prime. Why? Because P is their intersection, so obviously P is contained in each one of them as a subset. But that just means, according to the definition of our greater than or equal to relation, that P is greater than or equal to every P prime coming from K prime. It will be, sorry, I wrote K prime. And this just tells us that P is an upper bound for K prime. In K, this in K part just indicates this fact that P is inside K, and it's an upper bound for all the elements of K prime in this sense. So yes, now we can apply Zorn's lemma on the partially ordered set K, because every chain has been proved to have an upper bound in K. Thus, by Zorn's lemma, K has A means at least one maximal element. It may have more than one, but there is at least one, which is maximal with respect to what? With respect to this relation. But behind this relation, the real meaning is that P is a subset of P prime. And that is why that maximal element, we write like this, is clearly minimal with respect to inclusion. So here the solution ends.